Hello there, and welcome to Mysteries of Earth, the Measureless Cosmos. How big is the universe compared to our galaxy? It's a question that seems almost childlike in its simplicity. Yet the moment you try to answer it, you feel the ground of certainty slip away beneath your feet. Our minds evolved to picture valleys, oceans, continents, scales we can cross in a lifetime. But the Milky Way is not a valley, and the universe is no ocean we can ever sail across. To even glimpse their dimensions is to stand at the edge of comprehension itself. Begin with our own home. The Milky Way stretches roughly 100,000 light-years from end to end. That number is easy to say, but what does it mean? A single light-year is the distance light travels in one Earth year, about 946 trillion kilometers. Multiply that by 100,000, and you start to sense the immensity. If a spacecraft could somehow travel at the speed of light, something our physics forbids for anything with mass, it would still need 100 millennia to cross from one galactic rim to the other. Even then, it would only have traversed our local island in space. Within this disk of stars lies an estimated 400 billion suns. Around many of them orbit worlds. Some are hot, airless rocks. Others may be ocean planets or icy spheres. Statistically, tens of billions of these worlds could be Earth-like, bathed in starlight within a habitable zone. To human intuition, such numbers feel limitless. Yet the Milky Way is just one galaxy among uncountable others. Picture our galaxy as a single grain of sand. Now imagine every beach on Earth, every desert dune, every hidden layer of ocean floor. Each grain would stand for another galaxy. Current surveys suggest at least 2 trillion galaxies populate the observable universe. If the Milky Way is a grain of sand, the universe is an entire planetary crust of beach, and that is only the part we can see. What we call the observable universe spans about 93 billion light-years in diameter, nearly 1,000 times the width of our own galaxy. This is not a fixed boundary, but a horizon created by the finite speed of light and the expansion of space. When we look out, we are looking back in time. We see nearby stars as they were years ago, distant galaxies as they were billions of years ago, and the faint microwave afterglow of the Big Bang itself, almost 13.8 billion years in the past. During those billions of years, the fabric of space has stretched, carrying ancient light outward even as it moves toward us. That's why the edge of our observable sphere lies far beyond 13.8 billion light-years. It's a horizon of both time and distance. Inside this sphere, our Milky Way does not sit at the center of all existence. We appear central only because light reaches us from all directions at once. Every observer anywhere would see themselves at the center of their own cosmic horizon. We have no privileged position, no cosmic throne, only our accidental vantage point on one of hundreds of billions of stars, circling a fairly ordinary galactic core. And still, this horizon encloses only a fraction of what exists. Beyond it stretches a realm forever beyond our detection. Space there recedes faster than light relative to us, not because it breaks the cosmic speed limit, but because space itself expands. Any light emitted now from those unreachable regions will never reach us. Entire chains of galaxies drift irretrievably away. Their stories are cut off from ours, yet they continue. In this sense, the Milky Way is both enormous and minuscule. Enormous, because it holds hundreds of billions of suns and spans unimaginable distances. minuscule, because it is a speck in a sea that may be infinite. We are like plankton, trying to comprehend the Pax Pacific, and then learning that the Pacific is only one droplet in an endless cosmic ocean. This perspective can be dizzying. All our histories, civilizations, and memories occur within a tiny corner of one galaxy, which itself is only one grain of sand in a cosmic desert. Yet there is also a strange intimacy in this vastness. The same physical laws that shape galaxies also shaped the atoms in our bodies. The iron in our blood was forged in the cores of long-dead stars. The calcium in our bones once drifted as interstellar dust. We are not separate from the universe. We are its expression at human scale, its consciousness looking back on itself. When you realize that, the question, how big is the universe compared to our galaxy, becomes more than a curiosity about distance. It becomes a meditation on perspective and belonging. The Milky Way gives us a local address. The universe gives us a context too vast to fully grasp. And the act of asking ties both scales together, the speck and the infinite. In the chapters to come, we'll travel outward from this starting point, comparing our galactic home to structures larger still, clusters, filaments, and the cosmic web itself, and then exploring ideas about what may lie beyond the limits of observation. Each step will stretch imagination further, carrying us deeper into the mystery of size, scale, and existence itself. The observable universe, our cosmic bubble. From our quiet corner of the Milky Way, the night sky looks like a dome of stars. But that dome is an illusion of distance and perception. What we actually inhabit is not a dome, but a sphere, a bubble of light and time stretching in every direction, as far as we can see. Astronomers call this bubble the observable universe. It is not the whole of existence, but rather the portion of the cosmos whose light has had enough time to reach us since the beginning. What does observable really mean? It is easy to imagine that the universe ends where our telescopes run out of power, as though beyond the faintest galaxies there is only blackness. But the observable universe is not a limit of technology. It is a limit of physics. Light travels at a finite speed, and the universe has a finite age, about 13.8 billion years. Because of that, there is a horizon beyond which the light from distant objects has simply not yet arrived. That horizon forms the edge of our cosmic bubble. Inside this sphere lies everything we can ever, in principle, observe. Galaxies, nebula, black holes, the cosmic web of dark matter, even the faint whisper of the Big Bang itself. Beyond it lies the unobservable, not nothing, but something forever hidden from us by time and expansion. The observable universe is like the circle of light cast by a lantern in the dark. The lantern doesn't end the night. It simply shows the part we can see. At first glance, this bubble seems to place us at the center of everything. Maps of the observable universe show Earth surrounded by concentric shells of galaxies, like a cosmic onion. It is tempting to read this as evidence of a special position, a remnant of old, geocentric thinking. But the truth is more humbling and more fascinating. Every observer in the universe sits at the center of their own observable sphere, and an astronomer on a planet orbiting a distant star would also map galaxies in every direction and see themselves at the middle. This is not cosmic arrogance, but cosmic relativity. The universe is not centered on us. Our viewpoint is simply centered on us. Why is this so? Because when we look outward, we are also looking backward in time. The Andromeda Galaxy appears as it was 2.5 million years ago. Quasars at the edge of our sight shine from an epoch when galaxies were still assembling. The cosmic microwave background That faint, cold radiation permeating space is a snapshot of the universe when it was only 380,000 years old, long before stars or galaxies formed. Light is not instantaneous. It is a messenger carrying the history of the cosmos to our eyes. And because every observer receives a different but similarly time-stamped stream of light, each stands at the center of their own personal map of the past. This time-traveling nature of light means that the observable universe is not simply 13.8 billion light-years in radius. During the billions of years it took for distant light to arrive, space itself expanded. The galaxies we now see at the farthest edge are not 13.8 billion light-years away. They are more than 46 billion light-years away today. In other words, our observable universe is about 93 billion light-years across. Even more staggering, beyond this horizon, the unobservable universe continues, perhaps infinitely. What we can see is a single cosmic bubble adrift in something far larger. Think of blowing soap bubbles as a child. Each bubble floats, shimmering, reflecting colors. Inside each, the world looks slightly different. Now imagine bubbles that are not small, but vast, beyond comprehension, overlapping yet isolated by expansion. Our observable universe is one such bubble. But unlike soap bubbles, there may be no edge you can touch, only a horizon, defined not by a physical wall, but by the finite speed of light and the stretching of space. This horizon is both a boundary and a bridge. It marks the limit of our direct knowledge, yet it also tells us about what lies beyond. The cosmic microwave, background, for example, is light released when the universe first became transparent. It arrives from every direction at once, forming a perfect shell around us. It is not a physical shell we could ever reach, but a sphere of information, a fossil light echoing from a time before stars. By studying its faint ripples, astronomers infer the density, composition, and geometry of the universe. In a sense, the horizon acts like a mirror, reflecting our cosmic infancy. Understanding this horizon also reshapes how we think about distance. In everyday life, if you drive farther down a road, the landscape behind you remains the same. But in cosmology, traveling far enough outward would take you not just to different places, but to different times. The universe is not static scenery, but an evolving story. Each step away from Earth is also a step back in time, a deeper layer of the cosmic past. What does this mean for our place in the cosmos? It means that our maps are provisional, our knowledge bounded. The galaxies we see near the edge of the observable universe may have already merged, exploded, or drifted beyond reach. Entire chains of cosmic evolution unfold unseen. We are reading only the first few chapters of a book whose later pages have yet to arrive. And yet, there is a strange comfort in this. The observable universe binds us, not by privilege, but by physics. Every creature on every planet in every galaxy lives inside its own bubble of light. Each is equally at the center and equally not at the center. We are united by our horizons, by our limits. In a universe so vast and impersonal, that is a profound commonality. The notion of a cosmic bubble also raises questions about what lies beyond. If our observable sphere is 93 billion light-years across, how large is the unobservable universe? Current theories suggest it could be hundreds, thousands, or infinitely times larger. Some models of inflation propose that our entire universe is just one pocket in a multiverse, a froth of bubbles, each with its own laws of physics. In that vision, the observable universe is not even a speck, but a spark on a wave of endless creation. Such ideas are speculative, but they remind us of an essential truth. The observable universe is a window, not a container. It does not box us in, but opens outward into mystery. By measuring its edges, we are really measuring the limits of our own perception. We are not mapping the universe. We are mapping what the universe allows us to see. The next time you stand under the night sky, remember this: every star you see is part of a single galaxy, and every point of light beyond those stars, faint smudges, invisible to the naked eye, is a galaxy unto itself, and all of it lies within a bubble of time and light expanding outward. RD, a cosmic sphere whose edge is not a wall, but a horizon of history. You are standing at its center, not because you are special, but because every being stands at the center of their own light. To grasp this is to feel a shift in perspective. The observable universe is vast beyond comprehension, yet it is also deeply personal. It is the record of everything whose light has touched us. It is our cosmic autobiography, written in photons. And like all autobiographies, it hints at chapters still unwritten, still unread. As we step into the next part of our journey, we will move beyond this personal bubble and explore the large-scale structure of the universe itself, the clusters, filaments, and voids that weave galaxies into a cosmic web. If the observable universe is our bubble, what patterns emerge when we zoom out to the scaffolding of the cosmos? And what do those patterns tell us about the nature of reality itself? Expanding horizons. Imagine standing on a high plateau at dawn. With every passing second, the light spreads farther over the land, revealing new hills and valleys that were hidden in darkness. In a sense, that is what our view of the universe is doing, except the plateau is space itself, and the dawn is the light of countless suns. Each second, our cosmic horizon pushes outward by a light second in every direction. The observable universe literally grows as the oldest photons of distant galaxies finally reach us. But paradoxically, even as our sphere of sight expands, the fabric of space stretches beneath it, carrying parts of the universe away faster than that light can ever travel. We live in a cosmos where our vision grows and shrinks at once, a bubble of knowledge that expands at light speed while the unknown recedes even faster. To understand this tension, we have to grasp two ideas at once. First, light takes time to travel, so each passing second adds a shell of newly arrived information. Second, the universe itself is not static but expanding. Galaxies are not flying through space, so much as space itself is growing between them. This means some regions are slipping beyond our reach forever, no matter how long we wait. The horizon we talk about in cosmology is not like a mountaintop horizon you could one day reach by walking. It's more like a mirage on a hot road, retreating as you approach. The universe's expansion ensures there are places whose light will never arrive, whose histories will remain eternally outside our view. And yet, right now, we're living in a moment of extraordinary cosmic fortune. Astronomers sometimes call it the golden age of cosmic visibility. In the current epoch, galaxies are still close enough that their ancient light can reach us, yet far enough away to show us the early universe in detail. Billions of years from now, that will no longer be true. If some far future civilization looks up at their sky, they will see a lonely cosmos, stripped of its past. The galaxies beyond the local group will have receded beyond their cosmic horizon. only their own merged supergalaxy will remain. The cosmic microwave background, our window into the Big Bang, will have been stretched to such long wavelengths that it becomes undetectable. It will be as though the universe was always dark and empty. Our current sky, crowded with faint galaxies, is a fleeting gift of time and physics. This idea of a shrinking future universe is hard to reconcile with the ever-expanding numbers you hear. Trillions of stars, billions of galaxies, tens of billions of light years. How can it be that space grows and our horizon grows, yet the reachable universe shrinks? The answer lies in the difference between observable and accessible. The observable universe grows because new light is constantly arriving from ever farther sources, but those sources are themselves being carried away by the expansion of space. Their present locations are now far beyond any signal we could send to them. We can see their past, but never touch their present. We are watching cosmic postcards from cities that have already drifted beyond the shore. Consider a ship at sea. Each day, messages arrive in bottles from islands you've never seen. The more time passes, the more bottles arrive, telling you about distant lands. But the currents are carrying those islands farther away, even as their bottles reach you. You learn more about them, yet you can never sail to them. That is our situation with the farthest galaxies. Light from their youth is just arriving, but by now, they're receding faster than light due to the stretching of space. No rocket, however powerful, could ever catch them. We are seeing only their ghost images from the deep past. This has profound implications for how we think about cosmic history. We tend to imagine the universe as a fixed stage, with galaxies moving on it like actors. But the stage itself is swelling. What we see is not what is out there now, but what was once out there. When astronomers plot the distribution of galaxies at the edge of the observable universe, they are plotting ancient light, not current positions. The real cosmos is vastly larger and more dispersed than the picture we carry in our minds. Our map is a time machine. And yet, within this strange situation, there is opportunity. The expansion of our horizon at 1 light second per second means the universe is slowly revealing more of its story to us. Each year, new shells of the cosmic microwave background are decoded. Each decade, telescopes capture fainter and farther galaxies. We are still unwrapping the earliest chapters of cosmic history. This is why missions like the James Webb Space Telescope are so transformative. They extend our reach deeper into the young universe before those signals fade beyond detection. It's as if we're reading a book whose pages are drifting away, even as we turn them, and we're racing to read as much as possible before it vanishes. Why does this golden age matter? Because it's temporary. In the far future, dark energy will drive an accelerated expansion, creating an event horizon beyond which no new information can enter. Civilizations then will have no evidence of the Big Bang, no record of the cosmic web, no sign that other galaxies ever existed. Their physics might tell them the universe is static and small. The true history of cosmic evolution, galaxies forming, merging, fading, will be gone. Only now, in this slim window of billions of years, can a species assemble a coherent picture of its origins. We are not just fortunate to be alive, we are fortunate to be alive now. This perspective also reshapes how we think about our role. We often frame exploration as a human project, but in cosmic terms, we are the universe observing itself during a brief moment of self-awareness. Our telescopes are its eyes. Our instruments are its memories. We are gathering a record of the cosmos that no one else may ever have. That record is fragile, dependent on our curiosity and our ability to preserve knowledge. In a sense, building observatories, storing data, and sharing discoveries are acts of cosmic conservation, saving the story of the universe for a future when the sky itself will have forgotten. There is also a deeper, almost philosophical lesson here. The expanding horizon is a reminder that knowledge is never complete. Even as we push outward, the unknown recedes. The more we learn, the larger the mystery grows. Some regions will always be beyond our reach, perhaps infinitely so. We are not masters of the cosmos, but participants in a vast unfolding. This can be humbling, but it can also be liberating. It means there will always be something new to discover, even within our own shrinking window. Look again at the night sky with this in mind. Every faint glow from a galaxy is a message billions of years in transit. Every point of light beyond the Milky Way is part of a story we are catching in fragments. We live inside a shimmering bubble of time and space, one that grows with every heartbeat, but whose outer rim is slipping away. This is not a tragedy, but a wonder. We are voyagers on a cosmic tide, glimpsing shores no one will ever walk, gathering light from places no ship can reach. And because this golden age is brief, our questions take on urgency. What can we learn about dark energy before it hides the universe from us? How far back can we see before the first stars ignite? Can we find evidence of other universes, other bubbles, before our own horizon closes? Each new telescope, each new survey, is a bid to push the horizon outward a little faster than expansion can carry it away. This chapter of cosmic history will not last forever, but for now, it is ours. For now, the sky is full of distant galaxies and fossil light. For now, we can measure, map, and marvel. The expanding horizon is both a gift and a challenge, a chance to know our universe while it is still knowable. In the next chapter, we'll step from our personal bubble into the vast structure revealed within it. The cosmic web of galaxies and voids, the great filaments and nodes that shape the universe's architecture. If our horizon is a sphere, what patterns lie inside? And what do those patterns tell us about how the universe was built? The baby picture of everything. If you could travel backward through time, past the rise of life on Earth, past the formation of our sun, past the birth of galaxies themselves, what would you find? At first, you might expect darkness. After all, the farther you go back, the younger and more chaotic the universe becomes. But eventually, about 13.8 billion years ago, you would arrive at a moment when the entire cosmos glowed like the surface of a star. This was not a single object shining in space. It was space itself filled with light. And then, almost instantly on cosmic scales, that glow became a fossil. The light decoupled from matter and began a journey that still continues today. That ancient radiation is what we now call the cosmic microwave background, or CMB, the baby picture of everything. Why is it a baby picture? Because it shows the universe as it was only 380,000 years after the Big Bang. In human terms, that's like an ultrasound image from the first weeks of development, rather than a portrait taken at birth. The CMB preserves the conditions of a cosmos still in its infancy, hot, dense, and almost featureless. Yet inside that uniform glow were tiny ripples in temperature and density, the first seeds of all structure to come. Galaxies, stars, planets, and people are the descendants of those ripples. Looking at the CMB is like looking at a grainy photograph of a newborn and realizing you're glimpsing the ancestor of everything familiar. But to understand what we're seeing, we need to imagine a universe before light could travel freely. In the earliest moments after the Big Bang, space was a seething plasma of protons, electrons, and photons locked together in a furious dance. Photons, the particles of light, could not move far without slamming into free electrons, scattering like headlights in a dense fog. This meant the universe was opaque. No light path that could travel any distance. It was as though we were trapped inside a glowing cloud with no way to see beyond our immediate surroundings. Then, as the cosmos expanded, it cooled. About 380,000 years after the Big Bang, temperatures dropped low enough for protons and electrons to combine into neutral hydrogen atoms. This event is called recombination, and it transformed everything. With electrons bound into atoms, photons suddenly had a clear path. The fog lifted. Light streamed across space for the first time, carrying with it an imprint of the conditions at that moment. That light has been traveling ever since, stretching with the expansion of space into the microwave wavelengths we detect today. When our radio telescopes tune to the right frequency, they are literally catching the glow from the dawn of transparency. What does this ancient glow look like? To our eyes, it would be invisible, because its wavelength is now in the microwave part of the spectrum. But if you could see microwaves, the entire sky would appear to shimmer with a faint, uniform glow coming from every direction. It's not coming from stars, dust, or galaxies. It is the universe itself. When scientists first detected it by accident in 1965, they thought at first it might be interference, maybe bird droppings on the antenna, maybe some local noise. Only later did they realize they were hearing the echo of creation. Today, satellite observatories like COBE, WMAP, and Planck have mapped the CMB in exquisite detail. What they reveal is astonishing. Across the whole sky, the temperature of this radiation is almost exactly the same, 2.725 Kelvin, just a few degrees above absolute zero. But hidden in that uniformity are minute fluctuations, differences of only 1 part in 100,000. Those tiny ripples are cosmic gold. They are the fingerprints of quantum fluctuations blown up to cosmic scales during the earliest instant of inflation. They show where matter was slightly denser or thinner, where gravity would later sculpt galaxies and clusters. In those delicate modeled patterns, we see the blueprint of everything. Think about what that means. When you look at the CMB map, you're not looking at stars or gas clouds. You're looking at the initial conditions for the entire cosmic web. Every supercluster, every black hole, every future planet traces its ancestry to a slight excess of matter in one of those ripples. The heavy elements in your bones and blood were forged billions of years later in stars, but the scaffolding that gathered the gas for those stars was laid out in that early pattern. We are literally written into the baby picture of the universe. This is also our most distant view. Beyond the CMB, the universe was opaque. No electromagnetic radiation can come to us from earlier times, because light could not yet move freely. The CMB is not just far away in space, it's far away in time. It is the edge of what we can see with light. You can think of it as a cosmic horizon, not a wall, but a surface of last scattering. Beyond it lies a realm we can only infer through other means, like gravitational waves or neutrinos. In a very real sense, the CMB marks the limit of our electromagnetic vision. And yet, within that limit, we can read an entire epic. The patterns of polarization and temperature in the CMB tell us about the curvature of space, the total amount of matter and energy, the rate at which the universe expands. From this relic radiation, we've deduced the age of the cosmos, the density of dark matter, and even clues about dark energy. It's as though you looked at a single photograph of a newborn, and from it could deduce the baby's genetic code, family tree, and future height. The CMB is that rich. There is something profoundly moving about this. We are creatures who evolved on a small planet around an ordinary star. Yet we have built instruments sensitive enough to detect whispers from the universe's first light. That faint glow you can't see with your eyes suffuses every inch of space. It passes through your body right now. Countless photons per second, carrying information from a time before any star had yet shone. The night sky you admire with your eyes is only the foreground. Behind it, invisible, lies the baby picture of everything. But this photograph is not frozen. Because of cosmic expansion, its light has cooled and stretched over billions of years. In the far future, as dark energy drives galaxies farther apart and the universe grows colder, the CMB will fade into wavelengths too long to detect with any conceivable technology. Civilizations born trillions of years from now will look up at an empty sky and have no evidence of the Big Bang. They will never know they live in an expanding universe with a hot origin. Our cosmic baby picture will be gone, erased, not by time, but by expansion. This realization adds urgency to our studies. Right now, we are in a privileged era. The CMB is still strong enough to measure. Its patterns are still within reach of our detectors. We can still use its subtle features to test theories about inflation, quantum gravity, and the very birth of space-time. We can still hope to find in its polarization the signature of primordial gravitational waves, a direct clue to the first instant of the universe. This is our chance to decode the baby picture before it fades. And there is another, deeper lesson. The CMB shows us that the universe was once astonishingly simple, nearly uniform, smooth, and hot. From that simplicity emerged all the complexity we see today. The story of cosmic evolution is the story of how slight imperfections grow into stars, galaxies, planets, and minds. It's a reminder that structure arises from fluctuation, that diversity springs from subtlety. In a way, our own existence as conscious beings is encoded in those faint ripples of microwave light. When you think about your place in the cosmos, you might picture yourself as a speck on a small world in a vast galaxy. But go back far enough, and you were part of that glowing plasma, your atoms still unformed, your future written only as a slight overdensity in a sea of energy. The CMB is not just the baby picture of everything. It is our baby picture too. We are looking at our own origins when we look at that ancient light. And just as a baby picture hints at the adult to come, the CMB hints at the unseen universe beyond. Its patterns whisper about inflationary epochs, about possible multiverses, about physics we have yet to discover. It's the first page of a book whose later chapters we're still trying to read. The faint noise in our antennas is telling us a story older than stars, a story still unfolding. As we close this chapter, hold that image in your mind. The entire sky filled with invisible light, a perfect sphere of ancient photons surrounding us, carrying the memory of when the universe became transparent. This is the oldest, farthest thing we can see, and yet it's all around us, bathing every particle of our world. It is the baby picture of everything, a reminder that even the vastest structures once fit inside a simple, glowing cosmos. In the next chapter, we'll turn from that infant image to the scaffolding it foretold. The vast cosmic web of matter stretching across billions of light years, where galaxies trace the filaments seeded by those primordial ripples. If the CMB is the blueprint, the cosmic web is the architecture built upon it, speed limits and stretching space. We humans like speed. We build faster cars, faster planes, faster computers. But the moment you step outside our planet and look up at the night sky, you confront a very different kind of limit, a cosmic speed limit woven into the fabric of reality itself. No ship, no signal, no particle can move through space faster than the speed of light. This is not just a rule. It is a law so deep that our very definitions of time and distance depend upon it. But here's the paradox. While nothing can race through space faster than light, space itself can stretch and grow at any speed it pleases. This strange duality is one of the most mind-bending truths in all of cosmology. Pause for a moment and picture a beam of light leaving the sun. It takes just over 8 minutes to reach Earth. To Pluto, that same light travels more than 5 hours. To the nearest star beyond our sun, it needs more than 4 years. In our cosmic neighborhood, those numbers feel huge. But they are tiny compared to the distances light must traverse when we talk about galaxies, clusters, and the edge of the observable universe. And yet, even across such unfathomable gulfs, nothing beats light at moving through space. This is why light is our yardstick, our cosmic messenger, and stopwatch rolled into one. So why can't anything move faster? According to Einstein's special relativity, as an object accelerates toward the speed of light, its energy requirement to accelerate further grows without bound. Push harder, and you get diminishing returns. By the time you're within a hair's breadth of light speed, you would need infinite energy to go faster. And infinite energy does not exist in our universe. In a sense, light speed isn't like a posted limit on a highway. It's more like the end of the road itself. Beyond it, the concepts of time, mass, and energy warp beyond recognitive. But here's where the story becomes even stranger. While nothing can outrun light within space, the fabric of space can expand. And expansion isn't like motion through a background grid. It's the stretching of the grid itself. Imagine dots on the surface of a balloon. As you blow air into the balloon, the surface expands. Each dot stays in its place, but the distances between dots grow. The dots aren't moving across the surface. The surface itself is stretching. This is how our universe behaves. Galaxies are like those dots, mostly at rest, with respect to their local bit of space, while the space between them swells. Because of this, there's no limit to how quickly distances can grow. In the balloon analogy, a dot on the opposite side of the sphere might recede from you faster than light, even though it's not moving through the surface. The same is true for galaxies. The farther away they are, the faster they recede. Not because they're zooming through space like rockets, but because the space between you and them is expanding. This is why we can say parts of the universe are retreating from us faster than light without breaking relativity. Now, let's go back in time. Our universe didn't always look like this. In its first fraction of a second, something extraordinary happened. Inflation. Inflation was not just expansion. It was expansion on steroids. tiny quantum fluctuations, smaller than subatomic particles, were blown up to cosmic scales. In less than a heartbeat, the universe went from smaller than an atom to something perhaps the size of a grapefruit, or larger, depending on which model you choose. Space was stretching far faster than light could ever hope to travel, and yet nothing was actually moving through space. It was space itself that was erupting outward, like a freshly struck bell resonating across reality. Why is this important? Because inflation explains some of the great puzzles of cosmology. Why does the universe look so uniform in every direction, as though distant regions were once in intimate contact? Why is space so close to flat, rather than dramatically curved? Inflation answers these riddles. Before inflation, everything was near enough to exchange energy and information. Then, as inflation took hold, those regions were flung apart faster than light, freezing tiny irregularities into place. Irregularities that would later seed galaxies and clusters of galaxies. And this brings us back to the question of speed limits. When we look at the cosmic microwave background, that ancient afterglow from 13.8 billion years ago, we're seeing a snapshot of a time when the entire observable universe was smaller than a grain of sand. Light from that epoch is only reaching us now. But because space has stretched so dramatically since then, the region from which that light originated is now tens of billions of light years away. This is why the observable universe has a radius of about 46 billion light years, even though it's only been 13.8 billion years since the Big Bang. The light had only 13.8 billion years to travel, but the target it was aiming for has been running away on a moving walkway the whole time. We can even see this effect happening right now. There are galaxies whose light left them billions of years ago and is only arriving today. But the galaxies themselves are now far beyond the distance light could travel in that time. We're seeing their ancient images, but if we could teleport to their actual positions now, we'd find them much farther away, in some cases, already beyond our future reach. As space continues to expand, more and more of the universe will slip over a kind of cosmic event horizon. Light they emit today will never reach us, no matter how long we wait. The expansion of space is carrying them away faster than light forever. This leads to a poignant realization. We live in a golden age of cosmic visibility. Right now, our telescopes can still detect the faint whispers of ancient galaxies near the edge of the observable universe. But trillions of years from now, if there are still astronomers then, the night sky will look empty. The galaxies will have redshifted into invisibility, and the cosmic microwave background itself will fade into darkness. The story of the universe will be much harder to read. We are, in a sense, privileged witnesses at a time when the cosmos is both old enough to be interesting and young enough to still be observable. Think about what that means for our place in history. We often imagine ourselves as latecomers to the cosmic party, tiny beings on a tiny world orbiting an ordinary star. And that's true. But we are also living at a moment of unique clarity. Our instruments can still gather the light of the first stars and galaxies, still trace the echoes of inflation, still watch the universe expanding in real time. We're like archaeologists who have stumbled upon a temple before it erodes into sand, a fleeting chance to see the grandeur before it's gone. The tension between the speed of light and the expansion of space also shapes our future ambitions. When people dream of interstellar travel, they often imagine breaking the light barrier, crossing the gulfs between stars, in a blink. Physics tells us that's not possible, at least not by moving through space. But if space itself can stretch, Could it also contract, or bend, or form shortcuts? Concepts like wormholes and warp drives are speculative attempts to exploit the flexibility of space rather than fight against it. Whether such ideas will ever work remains unknown, but they spring from the same insight. The real game is not speed, but geometry, and as our understanding deepens, we see that speed limits and stretching space are not obstacles, but clues. They reveal that our universe is not a static stage, but a dynamic, evolving arena. Distances grow, horizons shift, and our observable bubble changes from moment to moment. Every photon we catch is a time traveler, carrying a piece of the past across an expanding ocean to our waiting eyes. In the end, the lesson is humbling and exhilarating at once. Light may be the fastest thing in the universe, but even it can be left behind by the growth of space. Inflation took quantum ripples and painted them across the sky. Expansion continues to push galaxies into the darkness beyond our reach. And here we stand, on a small world circling a small star, measuring it all with beams of light and the ingenuity of our minds. The next time you look up at the night sky, remember, those stars are not fixed points, but participants in a grand ballet of expansion. The darkness between them is not empty, but alive with stretching space. And the speed of light, which feels like an absolute boundary, is also the key that lets us read the story written on the cosmos. As we move forward, our questions become sharper. If inflation once stretched space faster than light, what else might the early universe have done? Could there be relics of that moment still hidden in the sky? Could understanding the speed limits of light and the stretching of space point us toward new physics, new frontiers, new ways of seeing? In our next chapter, we'll travel from the grand sweep of expansion to the delicate fingerprints it left behind. We'll examine how the earliest structures formed and how today's cosmic web, a vast scaffolding of galaxies and dark matter, traces its lineage back to those first inflationary ripples. The universe may be expanding, but so too is our understanding, reaching outward like light across the void, dark energy and the shrinking future. We often imagine the universe as a stage, vast, empty, and still. Galaxies are the actors, moving and spinning, but the stage itself seems unchanging. Yet the real cosmos is nothing like that. The stage is alive. It grows, stretches, and accelerates outward, and the actors are being carried away on a tide they cannot resist. This accelerating expansion is one of the most astonishing discoveries of modern science. It suggests not only that our universe is far stranger than we thought, but that its future may be lonelier, darker, and more mysterious than its past. The story begins with a question that haunted astronomers for most of the 20th century. How fast is the universe expanding, and will gravity ever slow it down? When Edwin Hubble first measured the recession of galaxies in the 1920s, the prevailing picture was simple. The universe had exploded outward in a big bang, and gravity was the brake. Over cosmic time, perhaps it would slow, stop, and collapse, or perhaps it would expand forever at a decreasing rate. For decades, astronomers tried to pin down which fate awaited us. By the 1990s, new tools, especially the use of type EEA supernovae as standard candles, allowed researchers to measure cosmic distances and expansion rates more precisely. Two rival teams set out to answer the big question: is the universe slowing down? They expected to find evidence of deceleration. Instead, in 1998, both teams independently stumbled on a result so shocking it earned them the Nobel Prize. The universe was not slowing down. It was speeding up. This acceleration implied the existence of something entirely new, something acting like a kind of negative gravity, pushing space apart instead of pulling it together. Lacking a better term, scientists called it dark energy. The name is more a confession of ignorance than a description. We don't know what dark energy is. We only know what it does. It dominates the energy budget of the cosmos and drives its expansion to accelerate ever faster. To grasp just how dominant dark energy is, consider the cosmic inventory. Ordinary matter, the kind that makes up stars, planets, people, and everything we can see, accounts for less than 5% of the universe. Dark matter, invisible but gravitationally influential, adds another 27%. But the largest share, about 68%, is dark energy. In other words, nearly 3/4 of the cosmos consists of something we cannot directly detect, cannot bottle in a lab, and cannot yet explain. It is as though we opened a ledger, expecting to find a few small debts, and instead discovered an enormous, mysterious fortune in the margin. So what exactly is this force? Some theories link dark energy to Einstein's cosmological constant, a term he originally inserted into his equations of general relativity to maintain a static universe. Others imagine it as a dynamic field, like a cosmic fluid with changing properties over time. Still others propose that our understanding of gravity itself might need revision at the largest scales. Each idea carries profound implications. If dark energy is constant, the universe will expand exponentially forever. If it evolves, it might weaken or strengthen, leading to very different cosmic fates. We are, even now, just beginning to tease out the clues. The observable effects of dark energy are dramatic. Galaxies that are already distant are being swept away ever faster. Each year, the cosmic horizon, the farthest region from which light can ever reach us, grows. But paradoxically, the number of galaxies within our accessible reach shrinks. It's like standing on a beach while the tide goes out. The shoreline may extend, but the water carrying the ships drifts farther and farther away. Let's make this vivid. Today, our best telescopes can see more than 2 trillion galaxies scattered across the observable universe. Each is an island of hundreds of billions of stars, many with their own planets, perhaps even life. But as cosmic time unfolds, dark energy will stretch space so rapidly that more and more of those galaxies will vanish from view. Their light will be redshifted beyond detection, stretched to wavelengths so long no conceivable instrument can catch them. In 100 billion years or so, only a handful of galaxies, our local group, bound together by gravity, will remain visible. Everything else will have slipped beyond a cosmic event horizon, forever inaccessible. Imagine that future sky. The Milky Way, Andromeda, and a few smaller companions may have merged into a single, massive, elliptical galaxy. Beyond that, the heavens will be almost empty. No glowing pinwheels, no distant clusters, no faint smudge of cosmic structure, just darkness. To any astronomers living in that epoch, the universe will look static and small. The evidence of a Big Bang, of cosmic expansion, of dark energy itself, will be gone. They may have no way to know the grandeur we once glimpsed. This isn't just a poetic thought experiment. It's a real scientific prediction. We live at a special time, a cosmic dawn, when light from the early universe is still reaching us, and distant galaxies are still within sight. In the deep future, the universe will be largely unknowable. Cosmic history will have been erased from the sky by the very expansion that created it. Our current ability to map billions of galaxies, detect the cosmic microwave background, and measure the fingerprints of dark energy is a fleeting gift. We are cosmic archaeologists at the moment, before the ruins are buried forever. Dark energy also shapes the fate of cosmic structures. Galaxies bound together by their own gravity, like our local group, will stay together, despite expansion. But larger structures, clusters and superclusters, will be torn apart as the space between them grows faster than their mutual attraction can hold. Over unimaginable timescales, stars will burn out, galaxies will dim, and the universe will approach a cold, dilute state, often called the heat death. If dark energy remains constant, this is our ultimate destiny, not a fiery collapse, but an endless, ever-thinning twilight. And yet, even within this stark scenario, mysteries remain. Could dark energy change over time? Could it reverse, slowing expansion, or even causing a new contraction? Some speculative models predict a big rip in which dark energy's repulsion grows so powerful that it eventually tears apart galaxies, stars, planets, and even atoms themselves. Others imagine a cyclic universe, with expansions and contractions alternating over eons. Each hypothesis reshapes not just the future, but our understanding of the past. The truth is, we don't yet know. Every observation we make today, every distant supernova, every subtle fluctuation in cosmic structure, is a clue to the ultimate nature of this hidden force. There's a humbling lesson here. For centuries, humans assumed the cosmos revolved around Earth. Then we discovered we orbit the sun. Then we learned the sun is just one star in a galaxy of hundreds of billions. Now we know our galaxy is one of trillions, and that even those trillions are only a small fraction of what exists. And at the heart of this immensity is a force we cannot see, but that shapes everything. Dark energy reminds us how small our certainties are compared to the unknown. Yet it also gives our moment in cosmic history a kind of poignancy and purpose. Right now, we can still see the distant galaxies. Right now, we can still measure the accelerating expansion. Right now, we can still ask these questions with the evidence spread across the sky. In a sense, the cosmos is whispering its secrets to us, but only for a limited time. We are the lucky generation, the one with both the tools and the view to decode the message. So when you look up tonight, remember, the stars above are not fixed lights on a black canvas. They are beacons on islands being swept away by an invisible tide. Their light is ancient, their distance growing, their future separation inevitable. But for this brief window of cosmic time, you and I can still see them. We can still chart their positions, still measure the acceleration, still trace the outlines of dark energy's invisible hand. And as our understanding deepens, new questions emerge. If dark energy dominates the universe, what role did it play in its birth? Could it be linked to inflation, that first furious expansion? Might there be subtle patterns in the distribution of galaxies that reveal its nature? Could experiments on Earth, in particle accelerators, or quantum sensors, offer clues to this cosmic mystery? In the chapters ahead, we'll follow those questions further. We'll explore how the universe's earliest light carries some signatures of its expansion, how cosmic structure formed and evolved under the push and pull of gravity and dark energy, and what that tells us about our own origins. The night sky may be shrinking in our future, but our curiosity is expanding faster than ever. Each discovery, like a photon racing across billions of years, brings us closer to understanding not just the universe's fate, but our place within it. The Hubble volume, limits of influence. We live in a universe that is both dazzlingly open and quietly bounded. Through our telescopes, we see galaxies scattered like dust across a limitless expanse, but hidden in that view is a sobering truth. Most of what we see is already beyond our reach. Even as our instruments grow sharper, the cosmic current carries everything away faster than we can follow. To understand this strange situation, we need to meet one of the least intuitive ideas in cosmology, the Hubble sphere, or as some call it, the Hubble volume, the invisible bubble within which cause and effect can still connect us to the wider cosmos. Imagine standing in the middle of a vast lake. Around you, the water is calm, but far away you see ripples racing outward. You throw a stone, and ripples spread from your spot. If the water's surface were somehow flowing outward faster than your ripples can move, there would be a circle beyond which your waves could never catch up. The Hubble sphere is like that circle. It isn't a wall or a physical edge, but a speed limit drawn in expanding space. Inside it, signals, gravity, and future spacecraft could in principle reach other worlds. Beyond it, the expansion of space itself drags everything away faster than light can traverse the gap, and your influence fades into nothing. Where does this limit come from? It begins with the Hubble constant, the measure of how quickly the universe expands at different distances. Every megaparsec, about 326 million light-years, of distance adds a fixed amount of recession speed. Near us, galaxies recede slowly. Farther out, the same proportionality means they recede faster. At a certain distance, the recession speed equals the speed of light. That radius is the Hubble sphere. Its size today is about 14.4 billion light-years. In other words, draw a bubble centered on the Milky Way with a... This number is surprisingly small compared to the observable universe, which stretches about 46 billion light-years in every direction. Why the difference? Because the observable universe is defined by light that has already had time to arrive since the Big Bang, even from regions now much farther away thanks to expansion. Those distant galaxies were closer when their light began its journey. We are seeing a fossil record of their past positions, not their current locations. The Hubble sphere, by contrast, is about the future, what we can still communicate with or influence. Most galaxies we can see today have already slipped beyond that horizon. They are like ships we glimpse at dusk, their sails catching the last light before they vanish over the curvature of the sea. This distinction between seeing and reaching is crucial. Photons can still arrive from beyond the Hubble sphere because they left long ago, before expansion carried their sources away. But any light we send now toward those galaxies will never catch up. In effect, the night sky is full of ghosts. We watch their images, but the real galaxies are receding into invisibility, and any future message from us will always lag behind. That realization changes how we think about our cosmic neighborhood. Inside the Hubble volume lie only a few tens of thousands of galaxies, a small fraction of the 2 trillion we can currently map. Over cosmic time, even that accessible number will dwindle. As dark energy drives acceleration, the Hubble sphere will stop expanding as fast as the universe itself. More and more galaxies will cross that limit permanently. Eventually, only the gravitationally bound local group will remain reachable. Everything else will have drifted into a realm forever disconnected from us. Why call it a sphere or volume? Because from every point in space, the same phenomenon applies. You are always at the center of your own Hubble sphere. An observer in a distant galaxy sees their own bubble, with us receding away beyond their horizon. There is no privileged center, no cosmic fortress from which everything else flees. Instead, the geometry of space and the constancy of light's speed create this strange symmetry. Everyone is at the center of their own vanishing universe. Visualize it. Picture a cosmic atlas with concentric shells around the Milky Way. Within the innermost shells, galaxies are near enough for future exchange. In the middle shells, Light can still reach us now, but our own influence cannot reach back. In the outermost shells, not even ancient light has arrived yet. They are completely unknown regions, still hidden beyond our cosmic horizon. The Hubble sphere marks the moving boundary between the first and the second zones, between worlds we can share and worlds we can only watch. This concept also forces a shift in how we dream about interstellar travel. Science fiction often imagines ships leaping from galaxy to galaxy, but even with perfect propulsion, faster than any conventional rocket, no craft can outrun the expansion of space once a destination lies beyond the Hubble radius. It is not a matter of speed through space. The space itself is swelling, carrying your goal away like a receding tide. Unless some new physics allows shortcuts, wormholes, warp bubbles, or other speculative constructs. Most of the universe is not merely far away. It is fundamentally unreachable. There is something poignant, even eerie, about that. We are surrounded by uncountable galaxies, each perhaps home to its own stories, its own histories of star birth and death, maybe even its own versions of life. Yet most of those stories are already cut off. We can receive their ancient light, but never send a reply. We are like archaeologists sifting through letters from a civilization long vanished, knowing we can never write back. And yet, within our bubble, there is still richness. Tens of thousands of galaxies remain potential partners in cosmic dialogue. Our own local group, the Milky Way, Andromeda, Triangulum, and dozens of dwarfs, is destined to merge into a single massive system over the next few billion years. Other nearby clusters may remain barely within reach for a while. This is our true cosmic neighborhood, the region with which we share a possible future. The Hubble sphere also sharpens the sense of timing. We are alive at an epoch when the universe is still readable. The cosmic microwave background still bathes us in information about the first moments after the Big Bang. Distant galaxies still shine in our detectors. We can still map the large-scale structure, still infer the presence of dark matter and dark energy. But this is temporary. As acceleration continues, the cosmos will dim and empty. The evidence of its own birth will fade beyond detection. Any astronomers born in that far future may look up and see only a static, isolated galaxy with no hint of expansion, no trace of a Big Bang, no clue to the grander universe beyond. We, by contrast, live in a golden age of cosmic visibility. This realization lends urgency to our quest for knowledge. Every new survey, every deep field image, every gravitational wave detection is part of a time-sensitive archive of the universe. We are gathering fossils before the strata are lost. The Hubble sphere is not only a limit, it is a reminder that our window is open now, but not forever. There is also a philosophical undertone. In our everyday lives, influence feels immediate. Speak, and someone hears. Move, and the ground responds. But on cosmic scales, even the fastest thing we know, light, is slow compared to the growth of space. The Hubble volume reveals a truth about power and isolation. Even an advanced civilization may never reach beyond its own bubble. The universe is vast, but each island of matter is, in the end, mostly alone. And yet, this very limit also connects us to something larger. Because everyone everywhere has their own Hubble sphere, and because the laws of physics are the same in each, we can infer that the cosmos beyond our reach shares the same patterns we see locally. By studying the edge of our bubble, by measuring how galaxies cross the horizon, we learn about dark energy, cosmic geometry, and the fate of all things. The Hubble volume is not just a prison. It is also a lens, a way to decode the unseen. So when you think of the night sky, don't imagine a static dome. Picture instead an ever-shifting boundary, a sphere of influence expanding and yet losing ground, with light racing in and hope streaming out but never quite catching up. Inside that sphere, we are actors in a shared story. Beyond it, the curtain is closing. And as we move to the next part of our journey, keep that image in mind. The universe's vastness is not only about size, but about connectivity. What can touch what? What can know what? What can remember what? We've learned about the bubble we inhabit and how most of the cosmos is already slipping away. But there is also something left behind, a faint imprint from the earliest times, still reaching us from the very edge of visibility. That imprint is our oldest messenger, and it will be our focus next. The baby picture of everything beyond the horizon. Hidden universes. When you gaze up at the night sky, the darkness between the stars seems like an ending. Beyond the edge of your sight, you might imagine emptiness stretching forever. But modern cosmology whispers a more daring possibility, that our universe is not the whole of reality, but a single room in a mansion of unimaginable scale. Regions may exist beyond our cosmic horizon, where the rules themselves differ, where gravity is stronger or weaker, where light behaves differently, where the building blocks of matter are rearranged into unfamiliar patterns. This is the realm of hidden universes, the haunting suggestion of a multiverse. How could such a thing arise? The key lies in the strange physics of the very beginning. According to our best models, the universe did not emerge calmly and evenly from the Big Bang. Instead, it experienced a brief, furious burst of expansion, known as inflation. In less than a fraction of a second, space itself ballooned by inconceivable factors, smoothing out irregularities and stretching quantum fluctuations to cosmic size. This inflation explains why our universe looks so uniform on large scales, but it also hints at something even wilder. What if inflation never stopped everywhere at once? Physicists call this idea eternal inflation. Imagine a field of tall grass swept by gusts of wind. Some patches are flattened quickly, others stay standing longer. In the same way, different regions of the primordial inflation field may have stopped inflating at different times. Where inflation ends, a hot Big Bang begins, a bubble of space-time like ours. But surrounding it, inflation continues, generating more bubbles, each a separate universe. The process never fully halts. It keeps spawning new universes endlessly, like a cosmic froth boiling on an invisible stove. Each bubble is isolated by the ongoing expanse, receding from its siblings faster than light can travel. From inside, you would never see the others. To an inhabitant of one bubble, the sky looks just like ours. Stars, galaxies, and the fading glow of a Big Bang. Yet beyond the horizon, beyond the boundary of inflation's end, other bubbles bloom and drift away forever. This is not just poetic speculation. The same mathematics that successfully predicts the pattern of temperature ripples in the cosmic microwave background also allows for eternal inflation. And once you accept the mechanism, its consequences follow. Each bubble may inherit slightly different conditions from the inflation field, leading to different physical constants. In one universe, electrons may be heavier. In another, nuclear force is weaker. Some universes may be sterile, unable to form stars. Others may churn with exotic particles and bizarre chemistry. We live in one where the constants happen to permit stable matter, complex molecules, and ultimately life. But in the multiverse, we may be only one note in an endless cosmic scale. What would it mean if this is true? For centuries, humans believed Earth was the center of creation. Then we learned we orbit a star among billions, in a galaxy among billions more. Each step enlarged the stage and diminished our apparent centrality. The multiverse, if real, would be the ultimate dethronement. Our entire universe, with its majestic galaxies, its 13.8 billion-year history, its web of cosmic filaments, would be just one bubble among perhaps infinite others. And yet, strangely, this vastness could also explain why we are here at all. If countless universes exist, each with random parameters, then somewhere the right combination must arise for life. We find ourselves in that somewhere, because only there could observers evolve to ask the question. This is the anthropic perspective. We see a universe fit for life, not because it was designed for us, but because universes unfit for life have no one to notice them. It is an unsettling but oddly economical answer. Instead of one improbable universe fine-tuned to perfection, there may be a multitude of universes with every possible variation, and we are naturally in one of the rare hospitable pockets. But can we ever know? Our horizon is a hard barrier. Light from other bubbles cannot reach us. Even if a neighboring universe drifted close, the space between would expand too rapidly to cross. Yet some physicists speculate about rare collisions. If two bubbles formed near each other in the inflation field, they might have brushed or merged before separating forever. Such a collision could leave a faint scar in our cosmic microwave background, a subtle circular pattern, a bruise in the oldest light. Researchers have searched for these fingerprints in satellite data. So far, none are confirmed. But the idea remains tantalizing, a hidden echo of another universe imprinted on our own sky. The multiverse also stretches our sense of reality. If inflation spawns an infinite number of universes, then somewhere, statistically, a bubble exists nearly identical to ours. Same galaxies, same Earth, perhaps even someone very much like you watching a night sky and wondering about hidden universes. In another bubble, history may have unfolded differently. No dinosaurs, no humans. A different story altogether. In yet another, physics may allow life forms beyond our imagination. Infinity swallows every possibility. This can feel overwhelming, like standing at the edge of an ocean with no shore in sight. Yet it can also be liberating. In a multiverse, our universe is not a fragile one-off, but part of a grand tapestry. We are not on a lonely island, but one of countless archipelagos, even if we can never sail between them. Our curiosity connects us to this vaster reality. By probing the smallest particles and the largest scales, by testing inflation's predictions, we inch toward understanding a structure far beyond what our senses evolved to grasp. The multiverse is still a hypothesis, not a proven fact. Many scientists caution that it may remain forever untestable, a philosophical framework rather than a physical theory. Others argue that if the math of inflation and quantum fields leads inexorably to multiple universes, we must take the idea seriously, whether or not we can see them. After all, black holes were once theoretical curiosities. So was the expansion of the universe itself. Reality has a way of being stranger than our current imagination. Even if we never confirm other universes directly, Thinking about them reshapes how we view our own. Our cosmic horizon no longer looks like an ultimate limit, but like the inside wall of a bubble, with unknown realities beyond. Our physical constants no longer seem uniquely ordained, but perhaps randomly drawn from a larger cosmic lottery. And our search for meaning becomes at once more humbling and more profound. If countless universes exist, our actions may not echo across all of them, but within our own bubble, this one chance, this one thread of history, still matters immensely. Picture it. Beyond the last galaxy your telescope can see, past the fading afterglow of the Big Bang, space-time itself may be inflating endlessly, sprouting new universes like seeds carried on a cosmic wind. Each seed expands into its own sky, its own laws, its own story. We are inside one seed, looking out. The horizon glows faintly, not with emptiness but with possibility. And here is the most mysterious twist. Even if the multiverse is real, we cannot stand outside it to watch. We are like fish in one pond, inferring the existence of other ponds by the patterns of ripples on our surface. The very act of imagining the multiverse is a leap across an unbridgeable gap. Yet this leap may be essential. It pushes science beyond parochial thinking, beyond the comforting notion that our universe is all there is. It invites us to consider a reality that is both more complex and more generous than we suspected. So the next time you look up at the night sky, let your mind drift beyond the horizon. Imagine regions where the speed of light differs, where stars burn blue and cold, where time flows in unfamiliar rhythms. Imagine universes where gravity binds more tightly, or scarcely at all. Imagine a cosmic mosaic so vast that our entire observable universe is a single tile. This is not merely fantasy. It is one of the boldest frontiers of modern physics, arising from equations, not just dreams. We have journeyed from the comforting familiarity of our own planet to the edges of our cosmic neighborhood, through the Hubble sphere, and now to the dizzying speculation of hidden universes. What lies beyond them, if anything does, may be forever unknowable. But the journey itself transforms us. We learn that horizons are not walls but invitations. We discover that mystery does not end at the edge of sight. It begins there. And as we step into our next chapter, we turn from the outward infinity to the inward one, from the multiverse beyond to the deep time within. Because even as the cosmos may host endless other worlds, our own world carries its own hidden past, written in rocks, fossils, and the silent testimony of time. That hidden history will be our next destination: infinite hierarchies and fractal reality. What if everything we know, every star, galaxy, and cosmic web filament, is not the top layer of reality, but only one scale in a vast repeating hierarchy? What if our observable universe is as small as a single grain of sand in some larger structure, and within the particles that make up our own world, entire universes blossom unnoticed? This is the question of fractal reality, the unsettling idea that scale itself may be an illusion. We are used to thinking hierarchically. An atom sits inside a molecule inside a cell inside a body inside a society. Each level has its own rules, but emerges from the levels beneath. The cosmos appears to follow the same pattern. Planets orbit stars. Stars gather into galaxies. Galaxies thread into clusters. Clusters form filaments that stretch across billions of light years. At each step, complexity emerges from a deeper layer. But what if the pattern does not stop? What if the universe itself is part of something larger, and that larger whole is part of something still greater, without end? Cosmology already gives us hints of self-similarity. When astronomers map the distribution of galaxies on enormous scales, the picture resembles a vast sponge or foam with bright nodes and empty voids. Zoom in on a simulation of dark matter, and you see the same filaments and knots repeated again and again, like branches within branches. Mathematicians call such structures fractals, patterns that echo themselves on different scales. Nature is full of them. The branching of trees, the veins in leaves, the spirals of hurricanes, the roughness of coastlines. Could the entire universe be a fractal, a cosmic fern whose twigs mirror its branches, whose branches mirror its trunk? Some physicists and philosophers have speculated that even the Planck scale, the unimaginably small distance where space-time itself becomes quantum and foamy, might host its own kind of subcosmos. In this view, every particle we observe could be a portal to another universe, curled up beyond our perception. Likewise, our own observable cosmos could be nothing more than a substructure inside a still greater meta-universe. In a truly infinite hierarchy, there would be no ultimate top or bottom, only endless nesting. This idea challenges not only our sense of size, but also of information. If reality is hierarchical and self-similar, where is the blueprint stored? Does each layer encode the rules for the next, like a fractal equation generating an infinite coastline from a simple formula? Could the constants of physics we measure be the settings of a deeper pattern, information flowing downward and upward across scales? Some theorists draw analogies to holograms, a whole picture encoded in every part, each fragment containing the seed of the whole. Perhaps the cosmos is a holographic fractal, each region carrying information about all the rest. And then there is consciousness. Our minds evolved to navigate a middle world of meters and seconds, not quarks and cosmic filaments. Yet within our brains, networks of neurons fire in complex patterns, producing thoughts that can encompass galaxies. A tiny cluster of matter can imagine an infinite expanse. This alone hints at a strange symmetry between inner and outer worlds. Some mystics have long claimed that consciousness itself is fractal, nested layers of awareness reflecting a larger cosmic mind. Modern science does not endorse such claims, but the parallel is hard to ignore. Neurons to brains, brains to societies, societies to planetary ecosystems, ecosystems to biospheres. Could consciousness scale up just as matter does? Even in physics, information and observation play a profound role. Quantum mechanics tells us that particles exist in superpositions until measured. Space and time themselves may be emergent properties of underlying informational relationships. In such a picture, our universe might resemble a vast computation, its laws and constants determined by deeper code. Within that code, subroutines could spawn whole simulated worlds, a digital version of nested universes. The simulation hypothesis is a modern echo of an ancient intuition. Reality might not be what it seems, and our entire cosmos could be a level within something vaster. Does any of this leave evidence we could detect? Some researchers look for subtle patterns in cosmic microwave background fluctuations, hoping to find signs of self-similarity across scales. Others explore the mathematics of scale invariance, searching for universal laws that hold regardless of size. So far, the results are suggestive, but not conclusive. Yet, even the absence of clear evidence does not extinguish the question. When you peer into a fractal, you never reach a final edge. The pattern always continues beyond your resolution. Perhaps the cosmos is the same. Every time we build a bigger telescope or a higher energy collider, we only reveal another layer, never an endpoint. Consider a thought experiment. Imagine shrinking down into an atom until you pass through its quantum foam and emerge into another expanse of galaxies, each filled with planets, beings, histories. From the perspective of that inner cosmos, you have traveled outward, not inward. Now imagine zooming out from our own observable universe until its clusters of galaxies blur into a single particle inside a still larger reality. Outward and inward lose their meaning. The map folds into itself. In such a hierarchy, the distinction between microcosm and macrocosm dissolves. You are both an inhabitant of a universe and a component of something else's atom. The poet William Blake once wrote of seeing a world in a grain of sand. Perhaps he was right in ways we are only beginning to glimpse. What about time? In a nested reality, time might also be hierarchical. Our 13.8 billion year cosmic history could be the blink of an eye in a metacosmos, whose own seconds span trillions of our years. Conversely, within the quarks of a proton, a whole universe might live out eons, while only microseconds pass for us. Scale and duration become relative, like concentric dream layers, in which each level runs at a different speed. If such a structure exists, the beginning of our universe may not be absolute, but simply the point where our level budded off from another. Even if this grand fractal reality remains speculative, thinking about it changes our perspective. It erodes the comforting sense that there is a largest or smallest scale, a final frontier where questions stop. It also invites us to see continuity where we once saw separation. The branching of a river delta echoes the branching of neurons. The swirl of a spiral galaxy echoes the swirl of a hurricane. Patterns repeat because they arise from the same mathematics. We are participants in that pattern, not outside observers. The universe is not only out there, it is in here, mirrored at every level. And here is a subtle consequence. In a truly infinite hierarchy, meaning might also be fractal. The choices of a single consciousness could influence larger scales through chains of interaction, just as the flutter of a butterfly's wings can shape a hurricane in chaos theory. Conversely, vast structures beyond our horizon might shape the probabilities within our own lives in ways we cannot detect. We are both authors and characters in a story written on many scales at once. Does this sound too extravagant? Perhaps, but recall how many times reality has outstripped our imagination. Once, people thought the Earth was the universe. Then they learned of other planets, other stars, other galaxies. Each revelation expanded the stage. Why should it stop here? Why assume our observable cosmos is the final layer? The fractal hypothesis is simply the next question in a long tradition of questioning. Ultimately, whether or not nested universes exist, the concept offers a powerful metaphor for humility and wonder. It reminds us that our maps are provisional, our categories local, our scales arbitrary. It encourages a shift from seeking a single center to embracing an endless network of centers, each with its own observers, its own horizons, its own mysteries. And it suggests that the journey of discovery may be endless, not because we are failing, but because reality itself is inexhaustible. So as you look around at the world, at the veins in a leaf, the branching of a lightning bolt, the web of galaxies across the sky. Remember that you might be seeing hints of a deeper architecture. You might be standing not at the top or bottom of reality, but at one shimmering layer of an infinite crystal. The mystery is not only out there, beyond the edge of the observable universe. It is also in here, in the structures of your own mind and the particles of your own body. In a fractal cosmos, you are not separate from the whole, but a miniature echo of it. And this thought leads naturally to our next destination. If the universe may be infinite in hierarchy and scale, what about its origin? Could there be a unifying principle or source from which all these nested realities arise? A cosmic root feeding all the branches. In our next chapter, we will explore how the search for origins transforms once you leave behind the idea of a single universe and begin to think in terms of an endless, self-generating reality. Star stuff becoming self-aware. Across billions of years, the universe has been sculpting itself. Hydrogen born in the first instance of time, fused inside stars to make helium, carbon, oxygen, and iron. Supernovae scattered those elements into space, where they drifted and cooled and gathered again. Out of that cosmic recycling plant came planets, oceans, atmospheres, and eventually, us. When you touch your own hand, you are touching atoms forged in the hearts of stars. When you breathe, the oxygen you inhale is a relic of ancient stellar furnaces. The very thought forming in your mind right now is carried by electrical signals flowing through networks built from those same atoms. You are literally the cosmos thinking about itself. It is easy to forget this when we look up at the night sky and feel small. Against the backdrop of a galaxy 100,000 light-years wide, our entire species occupies a blue world orbiting a modest star in an unremarkable arm of the Milky Way. And yet, in another sense, we are vast. The molecules that compose our cells once belonged to exploding suns scattered across thousands of light years. Your body is a map of stellar history. Your DNA is written in the alphabet of cosmic chemistry. In you, the universe has become capable of remembering its own story. How improbable is that? For most of cosmic time, there was no awareness at all, just energy, matter, and the blind unfolding of physical law. Planets formed and perished, stars ignited and died, galaxies collided in silence. Only recently, in a thin sliver of cosmic history, did a species evolve with brains complex enough to trace light back across billions of years, to measure the microwave glow of the Big Bang, to map the filaments of dark matter. In that sense, our telescopes and detectors are more than tools. They are extensions of cosmic self-reflection. Through us, the universe peers into, its own depths. Pause and think about what that means. Each time you look at a photograph from the Hubble or the James Webb Space Telescope, you are seeing ancient photons that have traveled across the void for eons just to strike your retina. In that instant, the gap between observer and observed collapses. Light that began its journey before Earth even formed is finishing it inside the neurons of your brain. The act of seeing connects two ends of time, a star that lived and died billions of years ago, and a moment of awareness in you, right now. This is not only poetic, but scientific. The heavier elements in your blood were made in stars. The calcium in your bones, the iron in your hemoglobin, the gold in your rings, all produced in cosmic furnaces. Even the water in your body, the hydrogen in every molecule, is older than any star, born in the first minutes of the universe. We are not visitors to the cosmos. We are a continuation of it, a momentary condensation of its matter and energy into a form capable of wonder. Yet this realization raises deeper questions. If consciousness has emerged once, might it emerge again and again? Are there other beings in other galaxies also looking out at the night sky and realizing they are made of star stuff? Could the cosmos be full of minds, each a spark of self-awareness, each a tiny mirror reflecting the whole? Our instruments cannot yet answer these questions, but the very possibility reshapes our sense of isolation. We are small, yes, but perhaps we are not alone in being the universe awake. This perspective also changes how we think about time. Our lives are measured in decades, our civilizations in millennia. But the carbon atoms in your cells are billions of years old, and the photons streaming from your local star have been on their way from its core for tens of thousands of years before reaching its surface and de-shining upon you. In every heartbeat, you are connected to processes that dwarf human history. Recognizing that can be humbling, but it can also be empowering. If the universe has taken 13.8 billion years to produce a being capable of curiosity, then curiosity is itself a cosmic achievement. In this light, science is not just a human pastime, but a natural continuation of cosmic evolution. The same physical laws that built stars built neurons. The same drive toward complexity that produced galaxies produced minds capable of wondering about galaxies. When we measure cosmic background radiation, chart exoplanets, or send probes to the edge of the solar system, we are extending the universe's capacity to know itself. The data stored on our hard drives, the equations on our chalkboards, the stories we tell about our origins, all are the cosmos reflecting upon its own emergence. And perhaps that reflection carries responsibility. A star does not choose whether to explode as a supernova. A galaxy does not decide to collide with another. But a conscious species can choose. We can decide how to use the knowledge we gain, how to care for the small world that gave rise to us. In a universe where most matter drifts without thought, a mind is precious. The ability to understand may also be the ability to preserve. Some thinkers go further and speculate that consciousness could play a role in the universe's long-term fate. Could advanced civilizations one day influence cosmic evolution, guiding matter and energy on scales now unimaginable? Might intelligence be as fundamental to the universe's story as gravity or light? Such ideas are speculative, yet they flow naturally from the recognition that we are not separate from the cosmos, but expressions of it. If star stuff can wake up once, it may wake up many times, and its choices may ripple outward across scales we cannot yet imagine. All of this can seem abstract until you bring it back to the simplest gesture: looking up. The night sky above you is the same sky your ancestors saw. But do you see it armed with knowledge they did not have? You know that the faint smudge of Andromeda is another galaxy of 1 trillion stars, that the light of Betelgeuse has been on its way for centuries, that the blackness between stars is not empty, but humming with particles, fields, and dark energy. You know that you are not looking at something separate from you, but at the larger context of which you are a part. In that moment, awe becomes a form of understanding. So when you next step outside and let your eyes adjust to the darkness, remember, the photons striking your retinas began their journeys before human beings existed, before Earth itself coalesced. The atoms composing your body were cooked in stars and scattered across the galaxy before gathering again to become you. And the thoughts you form as you gaze upward are themselves patterns of energy shaped by those atoms. The universe has spent eons assembling itself into a being who can ask, how big is the universe? Where did it come from? What does it mean? In that sense, you are both question and answer. You are the cosmos, measuring its own scale, testing its own laws, glimpsing its own origins. You are star stuff become self-aware. And if this is true for us, it may be true for countless others, each on their own world, circling their own star. Perhaps somewhere, an alien sky hosts another being, looking up and wondering the same things. Each of us separate, but connected by the shared fabric of matter, energy, and curiosity. We may never meet, but our existence together transforms the universe from a silent expanse into a network of minds. This is where our journey in this series brings us, from the birth of atoms to the rise of awareness, from the first light of the cosmos to the eyes that now perceive it. We are small, yes, but extraordinary. We are a bridge between past and future, between inanimate matter and reflective mind. And standing on that bridge, we can glimpse not only where we came from, but where we might go. For the story is not finished. The same telescopes that reveal the ancient past also point toward the future. They hint at cosmic fates we do not yet understand, at the possible end of stars, at the heat death of space, or at new beginnings beyond our horizon. They hint, too, at the tantalizing possibility of life elsewhere, of other minds, of a universe more alive than we dare imagine. So as this chapter closes, the question turns outward again. Having glimpsed our origins, what will we make of our future? What will star stuff do now that it has become aware of itself? That is the mystery waiting beyond the horizon, the next story we have yet to tell.